direct your question. Shortly after we conclude, you can listen to a replay of this news briefing online. First up, we'll hear from Steve Altemus. Steve?
Thank you, Nilüfer. Well, good afternoon, everybody. Any time that you ship a spacecraft to Florida for flight and end up a week later operating on the moon, I declare that a success. I will say that we shipped out. We had a great processing down with SpaceX at the PPF, or Payload Processing Facility, with them. We went through wet dress rehearsal and launched on February 26th. Like they indicated, we had a 7-day mission transit to the surface. Now, we think that we've been very successful to this point. However, I do have to tell you that we don't believe we're in the correct attitude on the surface of the moon yet again. I don't have all the data yet to say exactly what the attitude of the vehicle is. We're collecting photos now and downlinking those, and we're going to get a picture from the Lunar Reconnaissance Orbiter camera from above, from orbit, and we'll confirm that over the coming days as we get that data down. I can say, though, that we are charging on the surface. We have commanding, uplink, and downlink from the vehicle to our ground network on the ground in 8 dishes in 6 different countries. So we are communicating. We can command payloads on and off. We can send commands to the vehicle, and we have powered down and done some power conservation steps as prudent measures to see how long and what objectives we can accomplish in the mission going forward. When we get that full assessment, we will then work closely with NASA, science and technology groups to identify science objectives that are of the highest priority. And then we'll figure out what the mission profile will look. It will be off nominal because we're not getting everything that we had asked for in terms of power generation, communications, et cetera. However, if you think about it, we flew our liquid oxygen, liquid methane propulsion system that we make in-house. We fired that 6 times during the mission and burned for a total of over 23 minutes. The last burn you saw today was 15 minutes long for powered descent. Each one of those burns, the team executed flawlessly, and the last 3 burns were done totally autonomously with single commands sent to the vehicle with hours ahead of time, in which we actually, the vehicle performed the last burn behind the backside of the moon. So incredible autonomy demonstrated by the propulsion system and the mission ops team. I would say our navigation profile, our algorithms, the 4 algorithms we use in order to determine crater recognition, or our optical crater recognition techniques that we use, performed great. It's really new technology that we've invented in-house to create this kind of precision navigation. We did have some challenges with measurements coming out of our laser rangefinders. Those are sticky little things like we had from the last mission, which we'll go dive into and understand why those measurements were so noisy. Tim might be able to talk about that a little bit better. But we've traveled over 1 million kilometers out to the moon. We did 39 orbits around the moon in the past 72 hours. That's essentially operating a data relay satellite in orbit with our own ground station network. So the ground system worked seamlessly with orbit determination, precision. You recall from the first flight that we had some trouble with orbit determination and getting a pinpoint accuracy of where we were in space as we got closer to the moon. We ended up getting confirming measurements from many dishes around the world. And so orbit determination, we can put anything in orbit with precision using our ground network now. So we've made considerable strides since mission 1. And the team is, like our white flight, Gene Krantz, came and visited us this weekend and told us he was impressed with our professionalism and competence. And so I can't say enough about the team and how they executed and carried themselves. And like always, they worked through any technical challenges we went. And we'll just have to do the reconstruction and figure out exactly what the attitude is in the location, and then we'll get on with the rest of the mission as we can. Thanks, Nilüfer. That's it. Nikki?
Yeah, thank you so much. I think we can all agree, particularly today, that landing on the moon is extremely hard. And Intuitive Machines 2 was aiming to land in a place that humanity has not been to before. And while, as Steve said, we don't know the exact location of the lander, we do know that it is returning data, and we look forward to actually being able to work with Intuitive Machines on a plan to return as much science data and technology data as we can during its stay on the moon. We knew going into this mission, as we do for all of our CLIPS, that these are very high risk, high reward, and that the risk will always be there since these are experimental missions. And it's kind of a new thing for us as NASA takes sort of an unprecedented step back. We let the U.S. commercial providers take the lead from start to finish on the missions, and we think of ourselves more as a customer on these missions. Our goal is to set American companies up to establish a lunar economy on the surface, and that means that even if it doesn't land perfectly, we always learn lessons that we can provide and use in the future. And at NASA, we're all not just about lessons learned, we're always about lessons applied. NASA's Commercial Lunar Service Initiative, or CLIPS, is basically a one-stop, all-inclusive delivery service to the moon, where NASA is just one of many customers that are along for the ride. And American companies are always at the forefront of the innovation and discovery. The CLIPS vendor is responsible for payload integration and operations, launching from Earth and landing on the surface of the moon. And I can absolutely say that Intuitive Machines did all of those things for us. And now we have 2 Texas-based landers on the moon, and that's a very exciting place, I think, for us to be. NASA Science is excited to partner with our Space Technology Mission Directorate counterparts to bring back both scientific and technology data in ways that we've never done before, using this cutting-edge technology that has now been delivered to the moon with Athena. We know we landed about 5 degrees from the moon's south pole on a lunar plateau called Mons Mouton. It's about the size of Delaware and about as tall as Mount McKinley. It is a very scientifically strategic location, and we're hoping that we will get some exciting data just because of its sort of origin story. It's 20,000 feet higher than any of the neighboring features around the lunar south pole, and it's believed to be untouched by any lunar impacts for billions of years. And we worked closely with our colleagues in STMD, or the Science Technology Mission Directorate, to actually sort of zero in on this location, because it really does provide opportunities for high-value, high-priority investigations and explorations informed by its unique characteristics. It does have a very large ring of craters that lie around its base, and they have those cliff-like edges that descend into areas of permanent darkness. So we're excited to see what science and what technology we can do. As Steve noted, we already have some data. We took data, we did health checks on the instruments on their way out to the moon, and so we've already kind of increased the technology readiness level of some of these technology demonstrations by actually having them work in this environment. And so that's exciting even before we get to the landing. So you are going to hear a lot more in depth from Clayton about the technology that we were really excited to have on there. As always, our goal is to look at what resources actually exist on the moon so that we can get ready to have our sustained human presence and then prepare to send our astronauts onto Mars. We always think of the moon lighting our way to Mars. So I'm really proud of this team, the Intuitive Machines team. I'm always really proud of my CLIPS team and of all the people, all the experimenters that trusted us with their amazing technology. I'm really, really proud that American companies continue to be at the forefront of innovation and development as we move forward to create this lunar economy. So congratulations to Intuitive Machines for putting a second commercial lander on the moon, and congratulations to our NASA teams as well. Over to you, Clayton.
Thank you, Nikki. So I want to start also by thanking Steve, Tim, and Intuitive Machines. Days like today are why we do innovation and discovery. They make those things possible. thanks to their work and their courage and commitment to what we're doing here, we will be able to live and work on the lunar surface with humans. We will be able to land humans on Mars. That work has to start with days like today. And as Nikki said, we're going to learn every time we go. Each payload we carry, each bit of data we get back, we continue to work with them. We also are very pleased to be able to work with the aerospace community in general, because it's going to be all of us that are going to figure out how do we do that living and working on the lunar surface. It's been a really great opportunity to work through the CLIPS programs, and we want to continue to be able to do that. I also want to thank STMD for leading technology development for the agency. This is a key part of what we do. Not only do we have scientific discovery, but the technologies, and we have those opportunities where we learn things that go beyond the technology's initial intent. And so that's part of what we do driving forward. So I want to make sure that that you're aware of that and we track all those things going forward. So as we go forward, we continue to work with U.S. industry. We continue to work with those partners and the contributions from our partners, because they're demonstrating the value of not only demonstrating technologies in space, but also opening up that economic driver for living and working on a lunar surface. That'll be a key thing. So when we get back to that point, and I'll use aviation as an example, there was a time back in the day when only the government and those crazy daredevils messed with those flying machines. Now none of us give a second thought to hopping on an airplane. We don't build airplanes, we don't run airlines, but we are a customer and user of those. That's how you can imagine space going forward. But somebody has to do the heavy lifting and learning. So with that, Tim.
Thanks, Clayton. They always point to the old offensive lineman about heavy lifting. That's kind of the way it works sometimes. I'd like to paint a little bit of a picture going back to Valentine's Day of last year when we launched Odysseus, Odie. And every day that we went in on that mission, it seemed like that vehicle was just trying to escape our grasp. And we had to put out brush fires and understand how the systems we'd built were really working in space. And so every day was a challenge on that mission. And then finally, we ended up on the surface and successfully communicating and operated for many, many days. After the mission, the team got together and we made a list of all the things we'd learned. What do we need to change for the next mission? And we had 65 items. 10 were critical. The others were, well, if we can get these in for IM2, we will. But if not, they can wait on IM3 and it's probably enough. We got all 65 of those in on this mission. We took a couple of days off after the previous mission. Then we got together, we do what we call a hot wash. And the first hot wash I did was on Project Morpheus when I was at NASA when we lost a vehicle. And then we did a hot wash of all the things we wanted to improve. And 8 months later, we're up and flying better than ever. So that was the experience kind of leading into spring of last year, April timeframe. These are all of the improvements that we want to make. Our orbit determination needed improvement. We had people flying around the world to improve our ground sites to give us better measurements. We partnered with NASA to have validation and cross-check data to make sure that our systems would work the way they're supposed to. We had issues that we learned on the way we controlled our engines that we wanted to test. Our thermodynamic venting system. Could we make that better? Could we make it work the way we want it to work? We ran into problems on the first mission with helium management. Helium is very important to our system for pressurizing our cryogenic methane system, also for RCS. And then we had measurements we wanted to make of craters that we weren't able to get in place on the first mission. So we had a lot of new technology we brought forward in this mission. And I'll be honest, I had a little bit of trepidation when we launched about what some of these new things and improvements might do in the system. It was a night and day operational difference. On day one, we gathered some data about our propulsion system, and then on day two, we fired the engine. Better than we'd ever fired it before. The comm systems on our Omni antennas, which aren't even designed to bring high gain data home, worked better than our high gain antenna had worked on the first mission. We get to the moon, our orbit determination was so precise that we were within a couple of kilometers in our 100-kilometer orbit, and we didn't even have to do a lunar correction maneuver that we had put in place because we had to do one in an emergency on the first mission. So it really had moved from come in on the day of operations and save the vehicle to grab your lunch pail, go in, do spacecraft operations as this magnificent machine called Athena moved her way to the moon. all the way into lunar orbit. And then really the last couple of days in lunar orbit, we were expecting a fully successful landing. We did see some noise on our landing sensors towards the end. Our crater recognition system, it's machine learning on board. How do you tell a computer to look for craters? Not only look for the craters, but identify which craters those are on the moon. Worked almost an order of magnitude better than we'd anticipated. So we had every reason to believe that we were going to come down and land, with all systems the way we wanted to. We're trying to evaluate exactly what happened that very last bit, but I would tell you the improvement from the last mission to the next mission, really in less than a year, when you consider the fact that you have to be at the Cape early, you have to be done with testing before that. We took a little bit of time off after working really hard on the first mission. That's building, improving, and shipping a new spacecraft to go to the moon in 9 months. And I'm incredibly proud of the team. I'm incredibly proud of how well this vehicle performed. And I will tell you, the future is bright for Intuitive Machines to land lots and lots of cargo on the moon. And I'm excited to do that in partnership with NASA.
Great. Thanks to our briefers for those initial remarks. We'll now open it up for questions. Again, if you're on the phone bridge, please press *1 to submit a question. Once your name is called, please state to whom you'd like to direct your question. If you find that your question has already been asked, please press *2 to withdraw it. Let's start in the room before we go to the phone bridge.
Gina Sinceri for Steve. You said off nominal, but what pleasantly surprised you that worked well today? Can you kind of put it, off nominally, yeah, but things worked. So what was it worked that said, wow, good for this, that?
Well, one thing that is very exciting, it's a high-stress moment, but when we initiate powered descent, that is a 15-minute-long engine burn with a full throttle profile from 90% of throttle down to roughly 20% of throttle. It has dynamic movements like, you're braking for hundreds of seconds, then you're pitching over and you're descending and you're throttling down. Very dynamic. And that's a nail biter because everybody's quiet. And if you looked at the control room, everybody's just sitting there steely-eyed, watching the burn go. That to me was an amazing moment to fly that profile with this propulsion system and these navigation algorithms that Tim was talking about, receiving this data, these machine learning algorithms that we've come up with, and watching that all work in harmony was interesting, was just fascinating. And I really think that is the moment that you have to have the courage, like Clayton said, to take this, be in this business, to be able to put it all on the line and say, this is going to be successful. And we're going to, if it's a little off nominal, we're going to pick ourselves up and we're going to try it again. We're going to keep doing that. And so when we see that we saw, for example, the hazard relative navigation call a diversion autonomously from our planned landing site, saying that we see slopes greater than 10 degrees and boulders bigger than a bowling ball, you can't land there, and diverted us from that landing site to another one autonomously. It's incredible. So I'm very proud of the nav team and very proud of the propulsion team and the whole spacecraft team because they built a beautiful machine that is working at the highest level. This is the pinnacle of engineering, of man and machine coming together to engineer something that's never been done before at a price point that seems unachievable. So we really did mature the system, and this was evidence of it today.
We'll keep going in the room.
Mark Carreau for Aviation Week and Space Technology. I don't know how you could describe the orientation of the lander as best you know at this point, if it's upright or leaning or tipped. I'm not sure, so that's why I'm asking. And the communications and the instrumentation, can you tell us maybe how far you've checked in to all of that and how much further you need to go to verify everything?
Well, I can talk about the communications part because I just left the control center before I came over here. What I can tell you is that all 4 of our radios were active, and we were switching through comm configurations to see what the best high bandwidth solution was. And so we were getting the first packets of data down. We were able to send commands, and those commands were readily accepted. All of our telemetry was clean. So really, unlike last mission where we had to figure out reverse polarity and bouncing off the moon, it looked like this time sending and receiving messages was fairly straightforward. The challenge the team was working through was how do we establish the high bandwidth, the data links, so you're not getting just telemetry, but we're able to bring down the images so we can really get a good picture of where we landed. So that was still in work, but it wasn't, of the 4 radios, 2 of them aren't working. How do we repatch this? It was, okay, I've got 4 clean radios. We're talking better on some antennas than others. What's the best combination of those to move into a high data rate?
As far as orientation goes, there's conflicting data that we saw. If you listen to the live stream, if it was in the control room listening to the voice, you heard the prop console, propulsion element console, call out that they had pressure in the combustion chamber, and that would indicate that the vehicle was upright. We had another conflicting measurement that the IMU, the Z direction, which is horizontal, was pointing upright. So that would say it was on its side. We went and said we found that there was gas in the combustion chamber that was giving us a false read that the engine was running but at idle, and we think that that was incorrect, and that in fact that IMU data is a piece of data that says that we're oriented somewhat on our side. But I want to get all the measurements and the pictures to really be able to explain to you the configuration of the vehicle. I don't have a good sense of that today, I'm sorry. I have to get more data from that.
Okay, we will head over to the phones next. First up, we have Marcia Dunn with AP.
Yes, hi. I'm sort of confused. Is the lander on the mountain plateau near the South Pole as desired? You said at one point that the location was unknown. So did you get anywhere near where you intended? And is there a chance that you could have crashed, soft crash, if there's such a thing? What's your thoughts about that? Thank you.
I believe we're in the vicinity of the intended landing site. I don't know exactly where we would be in relation to the landing ellipse that we had specified pre-mission with 50 meters accuracy. So that is what we want to get Lunar Reconnaissance Orbiter camera view to pinpoint the location. We believe that all of the crater recognition measurements that we took were within our crater map database, so that we knew we were on the right trajectory to head to the intended landing site. So we have some confidence of that. We just need to get the pictures from above to determine precisely where we are, Marcia. It's not a fact of blindly not knowing. We know generally where to look. It's just with the precision that we can report is what I want that piece of data from. Tim, anything to add?
Yeah, we're definitely on Mars Bhutan, and our pre-mission analysis was that basically if I could get a single crater fix before we lit the engine, a crater fix after we lit the engine, and a crater fix before we pitched over, that just 3 measurements would be enough for us to land within 50 meters of the landing site. And what we actually saw was 30 or 40 measurements before pitch over and then 1 late. And so we have more than enough information. And the way this works is it's kind of like a fingerprint. The algorithm looks out at the moon and it says, first of all, I'm a navigator, offensive lineman navigator. I'm a navigator by trade. And so the computer looks out and it says, where are all the circles? And those are easy to identify. Okay, here's all the circles. 280 circles, maybe, in one measurement. And then, okay, of those circles, which of those could be craters because they have the right characteristics of light on one side and dark on the other? It'll go from 280 circles to 20 or 30 potential craters. Then those potential craters go into a database search, which is very much like a fingerprint. Okay, how can I fit these circles together that matches the database of all the craters we're going to fly over in the moon? And then it'll pop out and go, here are 4 guaranteed craters. And then that goes back onto the onboard navigation system and it says, hey, is that close enough to where I think I am for me to refine where I'm going? And the answer over and over and over was yes. So if it was the wrong craters, the navigation system would reject them. And it would say, no, that's way off. It's on the other side of the moon. That doesn't match. And if there was the wrong craters, you'd think that the machine learning algorithm on board wouldn't be able to identify them. The fact that those were all consistent going all the way down means that we were absolutely on Mons Mouton, right? And so when we get a picture in a couple days, we'll be able to guarantee that. We're probably going to look at our radiometrics as well and see if we can't do a tracking pass. And, you know, usually you track spacecraft in orbit. We'll track the spacecraft on the surface. And we'll see what we get. A little bit disappointed because our precision landing target was a 50-meter landing site. We're probably outside of that, but absolutely on Mars Mouton.
All right, we'll take one more question on the line. Next up, we have Bill Harwood from CBS News. Bill?
Yeah, hey, thank you very much. For Steve Altemus, I mean, it sounds like what you're saying is that the best data you have, the indications from the IMU, that's indicating the lander did, in fact, tip over and is resting on its side. Am I interpreting that correctly? And if that's true, given your comms, you know, the power generation, the stuff that's facing Earth, can you say anything about how this might, if this is true, how this might affect your payloads? Thanks.
Yeah, the IMU measurement, it was the piece of data that gave us the most clarity. When we dug into the propulsion data, like I said, we kind of refuted that. So we think that's the case. I would like to get a picture, though, to know the orientation of exactly where the antennas are pointed, where the engine bell's pointed, where are the solar panels, so that we can figure out a power profile. We know we can communicate with the payloads. We can talk to them and command them on and off. So if we can figure out the orientation correctly with imagery, we can then develop a power profile, like I said, and then result in a series of priorities in the science and technology list that would allow us to capture some mission objectives for the mission. Turn on the drill, turn on the mass spectrometers, for example, sniff for water as we vent the LOX tank, for example, with the Hungarian sensor, the Pulley space sensor, or with M-Solo, the STMD Prime 1 drill package mass spectrometer. Nokia, we know we can talk on Nokia radios on today. So there's quite a number of objectives that we can meet. We just have to lay that out here over the coming shifts. We just went from the operational shift, Tim's shift, mission director for Blue Team, and handed over to the surface team, and the surface team will set those priorities and lay that out going forward. And certainly we want to talk to the CLIPS office and to STMD to understand what their priorities are, and then we'll all put those together into a mission package.
All right, thank you so much for that question. We will go back into the room.
I'm Seth Kovar from CW39 here in Houston. We're very interested as a newsroom in this story, but part of the reason is we have a Houston institution and Johnson Space Center and NASA, and then we have a Houston company and Integrated Machines working together. Is there significance to that for the local economy, the local workforce, or any kind of significance you can think of?
Yeah, I would say, Seth, thanks for the question. We began Intuitive Machines. I'm a former civil servant of 25 years from Johnson Space Center and Kennedy Space Center. We formed Intuitive Machines right outside the gate of NASA's Johnson Space Center. And we built a sense of community. We worked with the city of Houston and the Houston Airport System to build our Lunar Production and Operations Center at Ellington Field, the Houston Spaceport. We worked with our local community college, San Jacinto Community College, to develop a technician training program where we can train and certify aerospace technicians in machining, in electronics, in composites, and give them jobs, give them careers in aerospace, building spaceflight hardware. So we're very closely tied to this economic region in building out this lunar economy, right here in Texas, right here in Houston.
We'll do one more question in the room.
Eric Berger with Ars Technica. Two questions. First of all, for Tim, could you just talk a little bit about the power and data rates you're getting now versus like what you would expect from a perfectly nominal mission? And then maybe for Nikki or Clayton, if the spacecraft is on its side, I would imagine it perhaps depends upon which side it's on, but can the prime drill mission operate as intended, or is it not going to be able to drill unless it's in a vertical configuration? Thanks.
Yeah, power is interesting at the South Pole because it's impacted not only by the solar illumination and our consumption, but by the thermal environment. So the big variable that our team was trying to establish before we left was how much heaters are we going to have to run. And so if you notice when you look at our landers, some of the sides are painted white to reflect solar light, other sides are painted dark to absorb more heat. So the real variable in all that. But when I left the ops center, we had achieved charging. And so, looking at that, once we find out exactly what orientation we're in, we'll be able to figure out what the longevity is and how to plan that power. The big question is what the solar transit is really going to be. So it's one thing to go, I've got an IMU that indicates we may be on our side, but that clocking angle, that's going to be the most important thing, because that will dictate what the thermal profile is going to be as the sun continues to move around the South Pole, and the thermal profile will be the dominant thing, our power profile.
And I'll say that we'll work with IM on that orientation, because that'll be important. As you described, it depends on where the vehicle is in terms of that orientation. But there will be science and technology objectives that we'll go for once we collaborate with IM on not only the power, but the orientation.
Does the spacecraft need to be vertical, though, for you to operate the drill?
Well, if you can imagine a drill, you can drill from many angles, but it's more you put together a combination of things. Our teams have been working with IM, the on-site teams. These are our priorities, what we think we can do depending on the orientation. I can speculate, but I'd have to speculate for every possible orientation. So no, it doesn't have to be directly where it can drill straight down. There are other options we can use too.
All right, we will go back to the phone bridge for the next set of questions. First up, we have Kenneth Chang with the New York Times. Ken?
Hi, thank you. I guess this is for Steve and Tim. When during the descent did the telemetry start getting strange, and can you tell what was going wrong?
I think, Tim, you were managing the flight at that point. Why don't you give some insight?
Yeah, our laser altimeters, we tested those out. If you recall, on the first mission, we had an issue where they wouldn't fire. We tested those extensively on this mission, and we fired them on the ground before we launched at the Cape. We fired them in orbit at the moon to make sure we saw power pulses, and then we fired them again in the lunar descent orbit. And that's where we first saw that there was more noise in the system than we had anticipated. And so as we came around for the final approach, we were concerned about the noise we were seeing in those measurements, but at the same time we were seeing better than expected results on our crater tracking. And so the hope was that that noise would clean up as we got closer to the moon, because the signal to noise gets stronger. And so the way these systems work, you have a power pulse that comes back, and that identifies a range measurement. And so that's what we were monitoring on the way down, and it just remained noisy all the way until touchdown. So that's where we're going to look as we investigate, what impact that might have had on the system for doing the final sequence of landing.
Thank you so much for that question. Next up, we do have Micah Maidenberg. Micah?
Hey, good afternoon. Steve or Tim, any initial thoughts on IM-3 and if you'll need more time between 2 and 3 compared to between 1 and 2 to sort of work the issues today? And do you think the company can still make the IM-3 window, which I believe runs through early next year? Thanks.
Yeah, we'll run a process like we did for mission 1, which is called the hot wash, which is a review of all the data. We take the next 30 days from mission complete, whenever that turns out to be. We take the next 30 days and we review all the data and prepare a set of recommendations for what went well, what went wrong, what needs to be fixed for the next mission, and what can be deferred into block upgrades for future missions beyond the next one on the manifest. Right now, we're planning IM-3. I believe that's a mid-latitude mission that's scheduled for about a year from now. What we're doing is we may hold that mission. I've talked to Nikki about it, because we won the Near Space Network contract to put data relay satellites around the moon. And the data relay satellites that we're making want to be on that mission 3, at least one of them, to take advantage of that rideshare opportunity. So we're aligning the schedule to see when that satellite is ready, and the mission is on track to be ready, and put that together, and that'll be our landing date. The effects, or launch date. The effects of this mission on mission 3 are not yet understood. I have to go through that hot wash process.
Great, thank you so much for that question. We will go back into the room.
Hi, Jackie Waddles from CNN. Thanks for doing this. First, I think for Tim or Steve, can you just confirm, want to make sure I understand, have you confirmed the health of your payloads? Looking specifically at the rovers and the Gracie Hopper, do we know that those are healthy in one piece? And then a question, I think, for Nikki. Obviously, Firefly had a successful landing over the weekend, but these are very different landing sites. I'm wondering if you could just quickly compare and contrast for us, what the unique challenges were that Intuitive Machines faced here.
So the first part, we have some insight into some of the payloads by being able to command them on and off kind of thing. But visually, I'm not sure of that yet until we get some imagery, like I say. I don't know, Tim, if you got any better insight from your time on console here in the past few hours, but.
Well, that was definitely part of the process that they were working through with the NASA scientists. In fact, I walked out of the control center and almost got waylaid by a group of them running into the room to talk priorities. That was the first thing to check out, but I don't have the data yet on exactly what that health feedback was.
Thank you so much for your question. We will go.
Nick has a piece.
Sorry.
Yeah, so they are very different locations. I mean, with our CLIPS program, we actually land, the goal is to land all over the place. So to land by the equator on the far side at the South Pole, and just really to be able to characterize the moon. That's why when we choose the landings, they are different payloads that we carry because they are sort of, bespoke for where we actually want to go and the type of data, whether it's technology, demonstrations and proving technology, whether it's science and studying the sun, as somebody here likes to do. But whatever we have the different science that we put on. So they both have different challenges. I certainly don't want to make it sound like Firefly was an easy landing. Landing on the moon is hard. And the thing that I'm so proud of is not only with the CLIPS program are we creating this sustainable lunar economy, but it is heartwarming that what we've actually created is, I hope it's sustainable, but it's a sustainable lunar community. And, I really want to just give a lot of love to Intuitive Machines because they shared all of their data from Intuitive Machines 1 with Firefly. And I'm sure Firefly will be sharing all their stuff with Intuitive Machines as well. The same with Astrobotic. I'm not going to say who did what, but some people sent coffee, some people sent donuts, some for these events, just to show this community that we have with these providers. And so we all share in each other's successes and we all empathize with each other's challenges. And I think that is the power of what we're doing with the commercial lunar payload services.
Yeah, and I'll add to that just an example from this mission. Once we got into orbit, Firefly had already landed. And we were getting a signal interference on one of our radios, and we knew that one of our frequencies was close to theirs. So we called Firefly up and said, hey, listen, we're trying to land. You're already down. Can you help us out? And their response was, yeah, absolutely, not a problem. Now, it turns out we figured out that wasn't the cause, and so we were able to not have to ask them to do anything. But the sense of community, and anytime humanity puts a lander on the moon, it's a good day. And so they definitely lived up to that. They were willing to help us out. Happy to help them out in the future, too. So now, I am a navigator, as I mentioned, and we took some really, really great pictures flying over the South Pole. And even as a space person, I am like everyone else. I'm used to looking at the moon and seeing the bright part and the really dark part. The South Pole is different. It's this twilight space of shadows and grays that it was interesting. I'm really proud of how well our crater tracking system did in this very unusual lighting condition. So we'll get it next time.
Great words. Thank you so much. We will go back to the line. We have Jeff Faust with Space News. Jeff?
Hey, good afternoon. A question for Steve or Tim. How far off the sort of the nominal landing altitude can you be and still deploy the hopper and the rovers? If you are somewhat on your side, as you say, would it still be possible to deploy them in some way? Thanks.
Well, Jeff, we're going to look at that. Obviously, we need to know the orientation of which panel, ABCD of the hex is facing up, or what is it on a slope? It's pretty flat there, but what is the orientation? And we want to think about that. And what is the configuration, say, of the hopper with its propellant tank and its thrusters, and can we do that? I would love to try that and see if we couldn't fly that off the rail system. I'm not sure yet, though. There's more data to be gathered. We'll come back to you and talk about it. I'm sure we're going to come up with something interesting.
We have a few more questions on the line. Next up, we do have Joey Roulette with Reuters. Joey?
Hey, thank you. For Tim or Steve, Intuitive Machines seemed pretty confident that the laser rangefinders this time would work given the past issues. What went wrong this time? I know you guys have a lot of data to look at, but where do you think things might have gone wrong this time to see another problem occur? And for Nikki, sorry if you had mentioned this before, but if we do confirm that the lander's on its side, can we still do the NASA experiments or the drill? Like how does that restrict you then? Thanks.
The first indication that the laser rangefinders, well, let me start at the beginning. I think Tim covered this mostly. We immediately fixed the safety enable switch on the laser rangefinders for mission 2. That was the problem that we had on mission 1, where we couldn't actually fire the laser because it was inhibited. This time, we immediately went back and put that enable wire into the harness and tested on the ground and fired the laser on the ground in a laser tunnel down into artificial regolith simulant and got the reflection back up and received it back into the laser rangefinder. So it was a complete test for the reflection back from the lunar regolith simulant. Then we went down to the Cape, we launched, and in right after lunar orbit insertion, we fired the lasers to get a pulse. We weren't low enough to look at the moon, but we got a pulse to say that the laser could actually be powered and fire. It wouldn't reach the surface because it's not rated to reach 100 kilometers down to the surface. It's rated at about 30 or 40 kilometers. So we needed to get down lower. So we got the signal that the laser rangefinders were firing. When we went into post-deorbit insertion down to a 100 by about 10 kilometer elliptical orbit, when we got closer, we fired the TRN laser, and then we rolled around and fired the HRN laser. What we saw on the TRN laser was these noisy measurements that Tim talked about. And so we decided with that one that we couldn't necessarily trust to automatically ingest those noisy measurements into the Kalman filter, which is part of the nav system. And it's weighted as how much you use and trust that altimeter setting. So we were going to ingest those manually. So we changed the trajectory to give us more time to evaluate those measurements, determine if they were healthy or noisy, and then we would ingest them in appropriately. The HRN laser, though, had an interlock signal. Now, we fired it in orbit, but an interlock signal came on when we tried to fire it post-deorbit insertion, which meant that it would not receive measurements, return measurements. So we waited, we cycled it several times. It actually came on very late in the trajectory, beyond the time we would have used it. We saw that interlock signal go off. So we think that there was either vibration or a thermal issue that caused the pin of sorts or a connector to get out of whack and get an intermittent signal. We know that we saw in a flat sat when we had a loose wire and you jiggled it, that interlock would go on and off. And so there was some event in space that caused that connection to get a little squirrely on us. And so that's kind of what we think at this point.
Yeah, and the differences between what we tested on the ground, it's really atmosphere, distance, and temperature. These are infrared lasers. And so now, instead of firing them over, a few hundreds of meters in one Earth atmosphere at Earth conditions, you're flying them at sometimes very hot, bright lunar surface, sometimes at very cold, dark lunar surface. It's in a vacuum and at much longer distances. And so we do the best we can to tune that out on Earth, but then when we got to the moon for the first time, we saw those lasers in operation. So that's definitely an area we'll look at going forward.
And yeah, thanks, Joey, for the question. We have already had some success. We've had the instruments on during the cruise phase, so we've actually been able to test them in that sort of area around the moon. We are excited about the fact, I know we've already had M-Solo on even today, and so we've actually had it working in the lunar environment, which is a big issue, a big thing for us. That's a big success, is to see these instruments on and working in the environment that they were designed for. Obviously, without knowing the exact orientation of the lander, it's hard to say exactly what science we will and will not be able to do. But we are excited. I mean, I think Tim kind of put it really well. He was nearly knocked over by a group of scientists ready to make the plan of what we can do. And we're very resourceful. NASA science is very resourceful. We do great science wherever we go in the universe, from the center of the sun to the edge of the universe. We do great science every second of every day. And so we are excited to continue to be able to do that. We will work very closely with Intuitive Machines to put together the plan to, obviously us space technology folks really anxious to get that going. All kinds of things we can do with a drill, even in a non-optimal orientation. So we're looking forward to hearing what exactly we have to work with, and then we will create a wonderful plan. Clayton, do you want to add anything?
Yeah, I'll just add that probably the reason Tim could escape is because the technologists were trying to get through the same door that everybody was going through. But Nikki makes a great point. Every bit of data, the fact that we could turn the instruments on in that environment was a plus. We learned something, and we'll continue to learn something. For two of them, they've already been turned on, so we know they work on the surface. And depending on the orientation and what we get going forward, we may be able to do even more. So I just can't foot stomp enough that every time we do this, every time we learn, we're closer to living and working on the lunar surface. And since the camera's on me, we're also closer to this. First day of school on Mars. So when we're comfortable as a society with our children going to school on Mars, it's because we will have done things with the aerospace community, companies like IM and Astrobotic, all those companies to help us do this thing, and it's in partnership with the government.
And I'll also note that the temptation for me, I like the images. I just heard Tim say they took amazing images of the South Pole from low altitudes. And so that for me is an incredible scientific achievement right there.
Thank you so much. We will continue on the phone lines. We have Jeff Brumfield with NPR. Jeff?
Hi there. This is a question for Nikki. I mean, we've had a couple, I guess if you look at this program at this point, we had a partial success, two partial successes, a failure, one successful landing, and you've just lost Lunar Trailblazer. I'm wondering if you're questioning this low-cost approach to doing business, outside of low Earth orbit right now, or if you still think this is the right way to go and you're getting your money's worth.
That's a great question. It is. I mean, it's difficult. We want to try and balance the what we do. We want to have a balanced portfolio, which is what we have in NASA science. So we do incredible science with CubeSats. We do incredible science with the James Webb Space Telescope and everything in between that. And so really, it is continuing to work very closely with our U.S. companies, whether it's with CLIPS, whether it is with our small Class D missions, which of course Lunar Trailblazer is one. And yes, we're very, we do watch Lunar Trailblazer very carefully. I also know that Intuitive Machines actually helped provide some data for us. So thank you on the way up for Lunar Trailblazer. The team there is extremely, extremely committed, working really closely with our folks at the Deep Space Network. If anyone can recover this spacecraft, the Lunar Trailblazer team can do that. But we do continue to look at our successes. We do have a lot of Class D missions that are very successful. We have another mission actually ready to launch on the West Coast right now. We have SphereX, which is a Class C mission. On that ESPA ring beneath it is a Class D mission called Punch, which is 4 spacecraft that are going to go and study the sun. And just a few days after that, we have a wonderful little mission, which is 3 CubeSats that are going to study the auroral electrojets. It's called EASY. It is a very, very small mission, and it is a unique mission because it's getting to a region that is too high for aircraft and too low for traditional spacecraft. And so we continue to lean in to these missions. We celebrate, as I said, about the CLIPS community, our Class D community. We get together, we celebrate one another's successes, and we empathize with one another's challenges. And so we will continue to push forward. We have Escapade coming, which is 2 spacecraft. It's the same program, the same simplex program. That mission has been ready for a while. 2 spacecraft built by Rocket Labs and launching launching with Blue Origin on a new Glenn later this year. So we continue to put a lot of focus on the work we do with our U.S. companies, and the goal, as always, getting more science into space for less money.
Thank you so much, Nikki. Next up, we have Issam Ahmed with AFP. Issam.
Hello. Thank you for taking my question. It's just for Tim and Steve. I think concerns were raised about the tall and slim profile, and as we saw compared to Firefly, which has the sort of short, squat design, that seemed to have worked out better. Do you think that played a role at all? I know you've been talking about issues with the laser rangefinder, and are there any sort of, on the flip side, what are the benefits that you gain from having the design profile that you chose? Thank you.
What I would say about our design is we fit out at the limits of the SpaceX fairing. So our landing gear extend as far out as possible to give us a stable approach. And contrary to what your intuitive thinking might think, that it's tall, so therefore the center of gravity has to be high. The center of gravity on this spacecraft was actually very low. We have heavy payloads low on the spacecraft. We have the hopper low. We have the helium tanks low. So the center of gravity was actually quite low on this one. So we know that didn't play a factor. In fact, it actually hurts our control system to fly with a center of gravity that low, and we had to work out slosh problems because of that, because we were exciting the slosh in the tanks. And so we know how to control the vehicle with the center of gravity and the footprint that we have. So the benefits, though, for the spacecraft are significant. We can fly a hopper because we can fly it off the side of the vehicle on a set of rails where it launches, fires its rocket and launches off these rails and separates from the lander. The height of the lander allows that. Also, our lander was conducive to fly the Prime 1 drill suite because we could deploy with the drill mechanism to lower it to the surface and then drill down. That's a long, tall drill, and so it fit neatly in the packaging of our deployment mechanism. In addition, we could develop a rover deploy mechanism that was tucked on the side and would deploy down to the surface. Again, those are all long mechanisms that were suited to our lander quite a bit. So we're confident in the design, we're confident in the engineering, and certainly the CG is a first-order base physics problem that we have solved.
Great, thank you so much. We do have continued questions on the line, but we only have a few minutes left for questions. We'll continue on with Jishnu Nair with the Houston Business Journal. Jishnu?
Hi, this one's for Steve and Tim. Just kind of following up on some of the other questions about kind of payloads. Just from like a business-to-business perspective, wondering, what kind of allowances are built into, contracts for payloads like the Lunar Outpost rover or other kinds of payloads if their time on the lunar surface ends up being shortened or compromised?
Well, in particular, the one you mentioned, Lunar Outpost, supplied Intuitive Machines a rover for our Nokia contract with Nokia Bell Labs. So if we can, it wasn't necessarily the objective to have the Lunar Outpost rover work. It was the objective to get the Nokia cellular technology to work at varying distances away from the lander. Both the rover and the hopper provided opportunities to do that. The way we do the contracts, though, we have certain language in there where, we're testing the envelope, we're testing the boundaries and the limits of what's possible. And so there are not necessarily repercussions. You don't necessarily make all the milestone payments, but there is no reflight clause necessarily, because this is a burgeoning lunar economy, and we have to foster an economy that can take the risk, to take the steps that are needed to actually make this happen. Much like Nikki talks about with low-cost science missions, it's important that we fly, and it's important that we learn. And that's what these contracts are written for, to allow for failures or missteps or contingencies. And so that's the business model today in a burgeoning lunar economy.
Thank you so much. Next up, we do have Lisa Grossman from Science News. Lisa?
Hi, thank you. I also wanted to ask about whether the rovers and the hopper would be able to be deployed, but it sounds like that's not something you can answer right now. Is there anything more you can say about that?
Well, you're correct. I really would like to get a little bit better understanding of the data and the pictures and images to fully assess before I commit to or say that we can't do something. We've got a very innovative team, and I think if given the time and the opportunity to study the problem, we'll come up with something.
Great. So we have time for 2 more questions. We will take one more on the line. We do have Marcia Smith with Space Policy Online. Marcia?
Could you talk just a little bit about the prime drill and how important that data is? If it doesn't work on this one, is it valuable enough for NASA to build another one? And if so, is the IM lander the only one that has the suitable size to fly it?
So the prime drill is another one of those technologies where we're learning how we discover not only from a scientific perspective, but how to live and work on the surface, right? What's in the surface, where there are resources like the ice, what is the regolith like, what can we get from the regolith? So we develop a series of technologies over time, and if we're certainly happy to share our roadmaps to say how we get to those answers. In this case, the prime drill was the exact right technology. Our colleagues at Kennedy Space Center developed the system. So we will pursue that data we need to get, but we'll do it in a number of different ways. So we learn every step of the way, and we'll keep pressing.
Thank you so much, Clayton. We will continue online. We do have Mike Wall with space.com. Mike?
Thank you, guys. Just a quick question for Yancy, either for Steve or for Tim. Do you guys know when is the next LRO pass? When do you expect to get those photos down? And is there any way you could confirm the orientation of Athena if you don't get that imagery as you're expecting? Thanks.
Yeah, I believe we're a day or 2 away from the next LRO pass, and then we already have a team looking at that opportunity. The number one thing is, after the first mission, we definitely added more cameras to this vehicle. So we have a number of cameras to choose from to help us visualize the horizon. We can get a lot of information, really the way humanity's done it for millennia, by looking at the distant horizon, seeing the Earth in the field of view. With that information, we'll be able to confirm orientation.
Great, thank you so much. And thanks to everyone who submitted questions today. And thanks to our briefers for taking the time to discuss Intuitive Machines' second moon landing enabled by the agency's Commercial Lunar Payload Services, or CLPS initiative. We hope you'll continue to follow along the mission on Intuitive Machines' platforms, as well as nasa.gov/CLPS. Thanks again for joining us. That will wrap today's briefing.